Welcome to CO450 Computer Architectures. This is week 11. So first of all, we're just going to do a little recap on the exercises for weeks 9 and 10. So we'll go over to the exercise sheet for this week and just have a look at some recap exercises just to make sure that you're familiar with what we've already covered. So let's go to the exercise sheet. So this is the exercise sheet for this week, and we've got a recap on truth tables to start with. So in this one it says create a truth table for the following logic expression. So we've got our expression here, so f equals not b and a and b, or not c and d. So we've got an and we've got a not here. So we've got a few things to work through. First of all, we need to put in our combinations of the 4 inputs. So with 4 inputs, don't forget we've got 16 rows to have 16 different combinations, and we just use our pattern of bits. So a 0, 1 pattern for A input there, which we can just copy and repeat all the way down for the 16 rows. If I can get Word to behave itself. So let's just put those in first. And then for B, we remember it's powers of 2, so it's 1 and then 2. So we have 2 zeros followed by 2 ones. And again, if we copy that and continue that pattern down. Oh. Continue that pattern down here. There we go. And then for C, it'll be, so we go 1, 2, and then 4. So 4 zeros followed by 4 ones. And that will repeat. In fact, rather than mess around with the copy and paste, I think I'll just put them straight in. There we go. And then finally, for D, we're going to have 8 zeros followed by 8 ones. Okay, and that's just a quick way to get all the patterns of binary input for all the different inputs, all the way from 0, 0, 0, 0 at the top to 1, 1, 1, 1 at the bottom. And here we have a combination in between. So always remember those patterns. So it's powers of 2, 1, 2, 4, 8. And obviously it would go 16 and keep going as more inputs you have. And the number of rows is governed by 2 to the number of inputs. So in this case, I've got 4 inputs, so 2 to the 4 is 16. So it's 16 rows that I have to continue those patterns down for to do my truth table. So hopefully you've got the hang of that so far. So now we need to evaluate parts of our expression. So we need not B. So not B is the inverse of whatever B is. So B here starts off with, it's a pattern of 0, 0, 1, 1, and so on. So we just need to reverse that pattern. So it's 1, 1, and then 0, 0. And then 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. So that's not B. And then we've got A and B. So if we look at A and B, remember with an AND gate, you can only get a 1 if both or all of the inputs are 1. So both of the inputs in this case, because we've only got 2 inputs, if both of them are 1, then we'll have a 1 as an output in the AND A and B column here. So we've got 0, 0 to start with, so that's 0, 1 and 0, 1 and 0. All right, here we go, 1, 1, so that's an output of 1. And then we've got 0, 0, 1 and 0, 0, 0. Oh, we got another 1. 0, 0, 1 and 0, 1 and 0. Let's see where the pattern's going. There we go, 1 there. And that means that finally we end up with that. So that's the that's all the 1 outputs for A and B. Now we've got, because we've got this part of our expression built, so we've got not B and we've got A and B. Now we can do this bit, so not B and A and B. So we can look at these. So again, and is what we are looking for. So 1 and 0, 0. So again, all these, the output of the A and B and the not B must be both 1 in order for us to get 1 here. So that's 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Actually, it never gives us a 1 output on that side, so which is interesting. So no, so they never ever a combination where we actually have not B and A and B producing a 1 output. So it's all zeros. Interesting. So on the other side we have not C and D. So we first need to work out what C and D is, and then we can invert it. So C and D, looking at these ones here. So again, looking for where they're both 1. So not as a 0. So be careful if you're looking here, because you can make sure you're looking at the right columns. Or hopefully looking at the right columns. So this is all just zeros. I think it's 0 all the way down to there. Yep. And then we get a load of 1 1. So those ones are the 1 outputs. Okay, but we're going to invert this, don't forget. So not C and D, which means it just simply inverts what we just had. So all those zeros suddenly become 1s. And the 1s, too far, become zeros. Okay, now finally we can bring it together. So not C and D, and sorry, OR. So we're ORing with this one. So not B and C, A and B is being ORed with the OR gate there with the output of not C and D. So OR, we only need one of those outputs to be 1 to get a 1 output. So effectively, because this is output in all 0, and these are zeros here, it means it's going to be the same pattern. So this will be, all these will be 1. And then the last combination at the bottom there are zeros, because we have zeros on both sides, even for the OR. So that's it. So it reproduces that output, basically. Good, which actually, if you think about it, it automatically suggests a simplification to this circuit. So if you get an output like this where it matches the output of this, for example, is what you want in terms of the final output, the F output there, you could just use that. You wouldn't need all the rest of the complicated inputs, really, because you just need that bit. Anyway, that's interesting. So obviously this expression doesn't really mean anything. It's just made up for an example for you to work through to get used to taking an expression and turning it into a truth table. But incidentally, you could actually simplify that if it was a real expression that was doing real work. Anyway, that's a bit beside the point. So hopefully that one's makes sense, and you've done that one. Had the idea, obviously here we got one to build. So create a logic design for the following logic expression. So we've got an expression to build in the multimedia logic. So let's get multimedia logic on the go, and we can go that. So F equals A or not B or not C and D. So we've got 4 inputs, A, B, C and D, and A, B and C are being ORed together and then ANDed with D. And whilst having not B and not C. Okay, so we need to build that in multimedia. Let's go over to multimedia logic and build that. Okay, so here we are in multimedia logic, and we need to build that circuit. So we had OR gate with 3 inputs. So 3 input OR gate. And we had some NOTs in there as well. So I think we had A, let's do the A input, A or not B, wire that one in, or not C. And then the output of the OR we were bringing together with the AND gate and input D. So A or not B or not C and D, and then the output going to F. So that's our circuit there for that expression. Okay, let's go back to the exercise sheet. So that was the expression we just built. So F equals A or B or not C and D. Let's continue on through to recap. So now we're recapping on sum of products and product of sums expressions, SOP and POS expressions, and we're doing a circuit design from the specification. So what's the first question? So what is a fully defined SOP expression for the following specification truth table? Okay, so SOP, sum of products, we're looking for 1 as the output, and we're going to create some min terms. So this one and these two and this one are the outputs. So these are the min terms that we need. So we need to create an expression. Let's make equation, right? Okay. So let's do that. So open brackets. So we've got A, B, and C. So here we're looking for 1s, and these are all 0. So we have A is 0, B is 0, and C is 0. So in terms of sum of products, when you have all 0s like that, and we're looking for 1s, these are not what we're looking for. So it's not A, not B, and not C in this case, because they are 0s. So it's going to have to be that with obviously and, because in sum of products it's and's first level and then or's the second level. So let's create that. So I'm going to need some knots here to add in. Okay, right, so not A, and then an and, a dot, not B, and then another and that one's not C. And then end up brackets there. So that's the first min term for this output. It makes sense when you think about it. So if you have the inputs of 0, 0, 0, and they're not, then it means they're all going to be 1s. And when they're all landed together, you will get a 1 output. So that makes perfect sense if you think about it. So if you can't remember, for example, whether sum of products is 1 outputs or 0, then logically that kind of makes sense. If you're looking for 1s, then the 0s are not in this case. So I think so. Yeah, so remember, sum of products, you're looking for 1s. If it's not a 1, it's not as the input, and it's the 1 outputs that you're obviously concentrating on creating the min terms for. So I'm just to make it a little bit easier, I'm going to copy that, and then I can adjust it for the next one. So this one underneath, so the next one that's 1 output on the F, has a 1 as A, so that will be A, not B, not C, with and between those. So we can put that one together just by altering that little expression so it's A and not B, not C. And then the final one here is the one right at the bottom, which is all 1s. So 1s are what we're looking for. So that will be A, B, and C, like that. Oops. So there we go. A, B, C. That's it. So that's our min terms, and we've worked that out based on the 1 outputs. And now we have to put that expression together. So let's put it as an expression again, just to make it give me a head start on the expression builder in Word here. Just create that. So F equals there's the first min term already done, and remember the next level then is OR. Copied everything. Just copy that bit. There we go. So OR is the next level, and then we can bring that one in And the next one was just that, which is A. And finally, this is just A and B and C. Oops. There we go. So that's my full expression for this sum of products, my specification for my design. So those are the outputs I wanted. Where I've got ones, I'm looking for the min terms. I'm using sum of products, taking all the min terms together as my full expression, and then that's what I need to actually build. So let's go and build that in multimedia logic. Okay, so in multimedia logic, I've got my three inputs, A, B, C, and we're going to need a 3-input AND gate. So let's create that. And we're going to need 3 of those because we've got 3 min terms. So I'm just going to make copies of those. And then we're going to need some NOTs, 3 of those. I'm going to place here. And then it's just a question of, obviously these 3 are being brought together by an OR gate. So again, 3-input OR gate. And that will go off to our F output. So let's wire these up. So the first combination we had was all 0, 0, 0. So that's all NOT. So let's do these as all NOT. So NOT A and NOT B and NOT C. And the second combination we had was actually 1 as A, so 1, 0, 0. So A, and then NOT B, NOT C. And the final combination, the final min term, was just A and B and C. And then they were all second level OR. And that goes to our final output. So let me just move these around a little bit. Just to make it, or try and make it, because we get a bit slightly spaghetti junction when you're wiring up, but it will work without that. There we go. And again, we could test our little circuit here, run it as a simulation, and we can see all zeros on. We've got 1 as an output, so that's right. Turn that on, we make no difference because 1, 0, 0 is still our combination. 1, 1, 0 wasn't in our combinations, but 1, 1, 1 was, so we get that. And again, you could test out any other combination apart from those 3 will give you 0 or no LED light, basically. So you could run through and just test, but that does exactly as we designed it to do. Let's head back to the exercise sheet. So now we're looking at POS, so we're looking at product of sums expression, and this time we're looking for max terms. So remember, with product of sums, we are looking for zeros. So with sum of products, we're looking for 1s. With products of sums, we are looking for zeros. So let's see where we've got zeros. Zeros there and 0, 0. So we've got 2 max terms to create. So and because we're looking for zeros, A in the first max term there is 1, and then 0, 0. So this is going to be not A, but B or C. And remember, we use ORs first. So let's put that in. So I need to insert my expression, my equation. And we can build that there. So open our brackets. Oops, I clicked into it. There we go. Right. So not A. So not A or, and then it's B or C. And that's our max term for that first output. And then the second one, I'm just going to paste that one. So now we've got 0, 1, 1. So, so we do want A. But it's not B. So not B or not C. There we go. That's it. So now we can do the full expression. So we've got the first one there. So F equals not A or B or C. And then we're bringing them together with AND. So remember, second level in the product of sums is AND. And then finally, the final part, which I might as well, can I copy that? Yes, just about. Right, okay, so, oops, I didn't want to do that. Try that instead. There we go, better. So let's just copy that one into there. There we go. So A or not B or C. So F equals not A or B or C, and A or not B and not C. So that's the expression that we end up with, and now we want to design our circuit for that in the multimedia logic. So we're going to need 2 OR gates and an AND gate to bring them together, and 3 inputs, of course, A, B, and C. So let's go over to multimedia logic and build that. Okay, so back in multimedia logic, and we have A, B, and C inputs here, and we've got 3 NOTs, and we've got our OR gate, and we're going to need 2 of those, and we've got our AND gate, which is going to be connected off to the F output, and oh, that's actually only needs to be a 2 input AND gate, of course, because we've only got 2 max terms coming into it. Whoops, can't change it while it's wired, so just dewire it and then change it to a 2 input. Better. And then wire it back up. Okay, and that's going to bring them together at the end, so ORs into ANDs. And so in our first max term, we had not A or B or C. And then in the second one, we had A or not B or not C. There we go. And we should find that if we run that, so our combination of so A or not B or not C gives us, remember we're looking for 0, so that's off. Yep, that's correct. And then we also had what did we have? So we had A, not A, or B or C. So that one as well. So 0, so 1, 0, 0 gives us nothing, as does 0, 1, 1. were the two combinations that we had in our specification. Anything else will give us 1, of course. That's good. So that's the circuit built. Let's go back to the exercise sheet. So now in the exercise sheet, we're just moving on, recapping specified truth tables from sum of products or products of sums expression. So this is working the other way. So this time we've got our expression and we're just trying to map in the outputs of that expression back to the truth table. So this is a sum of products expression. So we're looking for ones. So where these are not A and B and C, for example. So here we have A and B and C. So that must have been this combination here was to give a 1 output. So A and B and C must, because they must be looking for 1, so that must be 1, 1, 1. And then we have not A, B, or not C. So we must see that as 0, 1, 0. So 0, 1, 0 is there. So that must have given 1. And then we had not B, A, not B, or C, and C there. So that must have been 0, 0, 1. 0, 0, 1, that one. And the rest must have been then zeros. Like that. And then underneath that, we've got one for product of sum. So this is working the opposite way around. So we're looking for zeros. So in this case, the first max term here in the first bit in brackets must be A must have been 0, B must have been 1, and C must have been 0. So 0, 1, 0 is the first combination that would have given us a 0 output, because remember, product sums is concentrated on zeros. In the second max term there, we had A, B, and not C, so 0, 0, 1 gave us a 0 output. And then finally, we've got not A, not B, not C. So that must have been 1, 1, 1. Was giving us a 0 output. And the rest were obviously 1 outputs. So you can go from the other way. So you can go from the expression to the truth table. So that was the recap. Let's go back to the slides before we get into these canal maps, because you need to understand something about those. Okay, so back in the slides. So computers and logic gates then. So computers don't process bits in isolation, but as words. So we know words are the number of bits in length. So you can have an 8-bit machine, a 16-bit, 32-bit, 64 bits, as we have now. Nowadays really is quite common. So that's the word length that's being processed by the processor on a computer. So 2 bits at a time is how the processing works. So when AND gate is applied to words, it is called a logical operation. It is not an arithmetic operation. So we're used to doing, we've covered binary arithmetic, for example, and taking 2 bits at a time and added them together. But in a logical operation, we're applying the logic of the gate. So in AND logic, we have to have all the inputs 1 to get an output of 1. So when 2 words take part in a logical operation, such as AND, the operation takes place between the pairs of the bits. So although we still see all the bits as being in a word length, so 16 bits, 32 bits, 64 bits, etc., you're only ever logically operating on 2 bits at a time as a logical transformation between inputs. So as the bits are coming into the inputs, they're being logically operated on 2 bits at a time. If you see, so all the 16 bits or the 8 or let's say 64 bits are coming in 1 at a time as a pair and being operated on and being spat out the other side, basically. So you can see you have some examples of those transformations taking place here. So we have an AND gate, 2 inputs X and Y coming in. We have an OR gate and we have a NOT gate there for inversion. Now obviously we're a NOT gate, we're just transforming 1 bit at a time rather than 2. So AND gate mask. So example in an AND gate mask. So bit B3 of a word A is being ANDed with bit B3 of word B to produce bit 3 of word C. So what we see in the table here is an AND operation, a logical operation. So we have two word lengths, which are only 8 bits, only an 8-bit system, 8 bits at a time, and they're being brought in. So B0, for example, is 0 and 1, and it's being put for an AND operation, so obviously 0, because you need both inputs to be 1 to get an output. So it's not the same as addition, where you'd have 0 and 1 is 1. Now we're doing an AND logical operation. So 0 and 1 for an AND gate would give us 0, 0 and 0 gives 0, 1 and 1, because both inputs are now 1, so 1 comes out the other side. And that's the only time when you'll get a 1 output with the AND operation. So in the table below, we're using AND and the following two 8-bit words, and our result of our AND operation in the table is a new word, which is C. So we transformed them logically. So why might we want to use this type of logical AND gate or any sort of logical operation like this? So well, as an example, you might wish to mask certain bits in a word by forcing them to be 0. So to do certain operations or functions or calculations, then you might need to actually force certain bits to change and transform. So in this example, we want to clear the leftmost bits of an 8-bit word to 0, and by ANDing word A with word B, where word B is a specific mask, that will work well to give us word C. So you can see we're using word B as a masking process. So B is specifically set up with all ones in the first 4 bits from the right hand side, and the last 4 bits are left at 0. Now what that means is, as we know, for a logical AND operation, where you have zeros, the only thing that you're going to get on the outside is on the transformation is 0. Yeah. So you can see there that word A, when it's being put through this logical operation of word B using as a mask, the leftmost bits, the 4 leftmost bits, are all set to 0, so we can only get zeros on the outside. What we get underneath the 1 bits in the mask of the word B is word C allows the bits to move forward, to come through unchanged. So you still have 0, 0, 1, 1 in those first 4 bits, but the leftmost bits have all been set to 0 because we had a word B all had zeros at that point, which gave us a mask which allowed us to clear those bits. We can also then use OR gates to control bit transformations as well. So in computer processors, we use a similar way to using AND gates. So the logical OR operation can be used to set bits in word C, again, to logical 1 bits. So in this operation, again, we had the same mask, 4 bits of 1, 4 bits of 0 in word B, but we're using an OR logical operation. So in an OR logical operation, where you have 1s, you must have 1s coming out on the other side as the F output. So here we see when we set our masking word B to all 1s in the first 4 bits on the right hand side, the thing that we got on the word C output was all going to be 1s as well. So we've been able to use it as a mask to effectively transform those first 4 bits to be all 1. The remainder bits, because we had zeros in that last 4 bits of our word B, that allows whatever the word A was to come through unchanged. So 1, 0, 1, 1 is just dropping through unchanged, because with the 0 there, it can only be whatever word A actually is. So if it's a 1 with an OR operation, it must come through. If it's 0, it must come through. So it's just masking out certain bits. And again, you might be sort of slightly puzzled as to why we'd want to use this. But at the moment, the key concept is getting across the idea that we can mask. So by using an OR operation, we can mask this way by putting our word B transformation in. By using AND, we can mask in a particular way. But don't worry too much about why you really want to do this masking process. Just the fact that you can do this masking process, because this masking process is used in computer systems, it's used in all sorts of things. We'll come across it again in networking quite a bit in the system module, because that's how we look at the subnet masks that we do for IP addressing and things like that uses masks in the transformation process. So this masking approach is a kind of key fundamental way of transforming bits, and you need to just understand the operation more than the application at this point. So what we can also then do, if you can mask once, you can mask again. So you can take, your word C and put it through another mask. So you can combine it with another word B to do something else. So in this particular example, we're applying both and or gate operations to a word, and we can selectively clear or set bits on the final output. So you can see here that I'm doing I'm not actually saying what the word is that we've put in, but because you don't really need to. So I'm just saying, put it for an AND word, whatever the word is, 8 bits come in, B0 to B7, and on the first iteration we go for an AND mask, and that AND mask is all ones up to bit 5, and bit 6 and bit 7 are set to 0, which means it will automatically, for an AND mask, make bit 7 and bit 6 and 7 become zeros. The rest of the word, whatever it was, remains unchanged. Now if we put that then through another OR operation, in this case an OR mask, if we put that through again, and the OR mask is set so that we have zeros apart from bit 5 and bit 4, which are set to 1, and by doing that we're setting bits 5 and 4 to 1. So whatever they were in the original word, they might have been ones already, but it could have been 2 zeros. We've set them to 1. So we end up with a pattern of bits in the last 4 bits as 1 1 0 0, and the first 4 bits as whatever the original word was. Now again, like I said, this is you need to understand the operation. Don't worry too much about the application at this point, but you must understand that this is allowing us to manipulate bits at the bit level by doing logical operations and an or masking process to actually do those transformations, and that's what is really important at this point. So so the NOT is a gate flip. So like both and OR operations, the NOT function can also be applied to words to effectively flip the bits passing through the NOT gate, an inversion. So here we could have done our transformation. So we've controlled our and our OR logical operations, and then finally we can apply a NOT gate at the end to invert, so it just flip everything over effectively. Now where do we see flipping? Well, we saw flipping as a useful way, as a little mathematical trick to do our 2's complement. So we said flip the bits and add 1. So flipping the bits is actually an application of a logical process. So with a NOT gate, being able to kind of flip those bits over and then add 1 to it. So straight away you can kind of see some potentials there if you're building logic circuits which are going to actually carry out mathematical functions within a computer. It's worth noting that there is a certain amount of gate delay in the sort of physical operation of these electronic circuits. So electronic circuits work obviously incredibly quickly. They work in the nanosecond range, fraction of nanoseconds. But it's important to understand there is, even in fast things like electronic circuits, there is still a delay. So it's not instantaneous. So in actual physical gates, if the input changes that causes the output to change, the output change does not occur instantaneously. The delay between an input change and the output change is the gate delay, which we see here. So we have time at the bottom in nanoseconds, incredibly fast, but we can see that as we are changing inputs and outputs, or changing inputs, the output of the circuit is slightly, it's not perfectly aligned, like it's not instantaneous. There is a gap of about 0.3 of a nanosecond between input coming in and output coming out, and that's just something worth noting in terms of the operation of these electronic circuits. So electronic circuits are not instantaneous things. There are physical limitations to how they respond. We can also see that sort of behavior over time. We could kind of map that out as we're trying to show here. So here we see sort of sine wave of our electronic outputs, and we can see that where the wave goes down to the bottom, we're essentially operating at 0 volts, so we are 0, and where it goes up to the top, we're operating at like 5 volts, so we're at 1. And ideally, you kind of have this perfect digital wave where we have inputs of X and Y coming in, and where those operations are being carried out on them through and or and not, that is also changing the output over time. So as you're applying the logical operations, the bits coming in are being impacted by the operations being set, and you can see that here in this kind of sine wave view as time travels and as the inputs come in and out. What I'm trying to really get to your over to you really is that things exist within certainly electronic circuits. They exist in a real-time space, and they are physical processes that have been manipulation of the electron flow through the electronic circuitry. So time and all those sort of things about physicality make a impact in how the circuitry behaves. So now we come to canard maps, which we also can abbreviate as K-maps. So a standard approach to simplifying Boolean expressions, which is what we've been concentrating on, is called the canard map, or K-map for short. A K-map is a truth table graph which adds or aids in visually simplifying logic. So it's a visual way to simplify our logic within our expressions. So we talked a little bit last week about simplifying. We had some theorems and we had De Morgan's law, which are useful and can be applied, of course. But now we're moving into an area of a visual table or graph, which can also help us to simplify. And these are actually relatively easy to use once you get your head around them. So it's useful up to 5 or 6 variables. Beyond that, it gets too unwieldy. So this is good for those sort of level of variables, but for bigger circuits or more inputs, then it would get too wieldy. That's where your theorems and your De Morgan's law really come into their own. So it's a good tool to help understand the process of logic simplification, and K-maps can be used for both sum of products or products of sums expressions to aid the simplification. So here we see a sum of products canard map, or K-map, and the diagram shows us a 2-variable sum of products K-map. So this is very simple K-map, demonstrates that an n variable K-map contains all the combinations of the n variables in the K-map space. You should note that the 4 squares represent all the combinations of the 2 K-map variables or min terms in A and B. So you'll notice on the diagram here, this is the way we use it in the table. We have one set of inputs on one side and another set of inputs running across the top. So it's a typical graph in that we have sort of X and Y, and in this case we're using inputs labeled A and B. So we start off in a sum of products because we're looking for ones at 0. So we have not A and not B here. Where they intersect is where we would create our min term. So this is the min term for not A and not B. So this would be F equals not A and not B. So remember, it's and in the min terms for a sum of products. So, and then we change the input for the next row down. So not A becomes A and not B becomes B. And that effectively would mean that we would have 0, 1 here, and F equals not A and B, and here it would be A, so F equals A and not B, and F equals A and B. So these are the separate min terms. So that's all 4 combinations. So with 2 inputs, we have 4 potential outputs, and those 4 outputs are mapped onto this graph, this table that we're creating. For products of sums, we can do exactly the same thing. but this time we're looking for zeros. So we start with, in this case, we've got just the two inputs again, A and B. So this time, of course, we're going to start with A or B. And again, that would be 0 or 0. So 0, square up here in the sort of top left corner. And we go down to the bottom right corner where it's all ones. So in this case, in a product sums, because we're looking for zeros, this must be not A and not B, or not B must be, that must be 1 or 1. So the 1, 1 squared there. So this is how we kind of draw out our product sums. And we're only dealing with two inputs here. Obviously, these start to get a little bit more combinations. So these are the combinations of max terms for A and B. Now this is another sum of products Canard map, and this one has 3 variables. So you can see that we've again mapped those out, and because it's sum of products, we've started with not A, not B, and not C. And again, the intersection of those row and column creates our first min term. And here we're actually we're just numbering the individual min terms. So we have 8 min terms because we have 3 inputs. So 2 to the 3 is 8. And all the possible 3 of the 8 min terms are represented here. And we're just numbering the squares. So I've numbered them. The blue are decimal numbers, and the blue are hexadecimal numbers, and the red are binary numbers. So you do the binary first. So not A, not B, not C in a sum of products must be 0, 0, 0. And then as we go across, we would have 0, 0, 1, 0, 1, 1, 0, 1, 0. So you can see the various different combinations. And if we convert those back to hex, then we have 0, 1, 3, 2, 4, 5, 7, and 6. So the ordering isn't like 1, 2, 3, 4, 5, 6, 7. It may vary a bit, but depending on the input combination for the individual min term or max term cell, depending on if you're doing sum of products or products of sums. So let's have a look at another 3 variable Canard map for product of sums. So notice we put the 2 with an uneven variables, as we've got with 3 obviously. Across the top we're putting 2, and we're putting 1 down the side. So it's important you draw out your Canard map. So I'm going to ask you you're going to have to do a draw out these Canard maps to use them on a bit of spare paper. So make sure you're familiar with the drawing out to make sure it's drawn out exactly as I've got them here. So they need to be drawn in the same way with the same inputs on there. So I'm only going to give you up to maybe 4 inputs. So you'll see examples of all those in a moment. So make sure you kind of command those to memory, and you can draw them out. So these are max terms. So again, we start off with 0, 0 in the top left. So with products of sums, obviously it's looking for 0. So A or B or C. And again, we can go across as we go. So we end up with 0, 1, 3, 2, 4, 5, 7, 6. So the numbering is essentially the same as sum of products, but this is for products of sums. So when moving horizontally or vertically in a sum of products or product of sums K-map, the only one variable changes between adjacent squares, never 2. So that's the important thing about this. The way that the variables are set up and they are numbered is because we are trying to get to a situation where as you move between one square and another square, you only change one variable. So in the case of everything in this row, not A stays the same. But as we move from not B, not C, for example, not C is the only thing that changes to C on that one. And as we move across, then not B becomes B. And as we move across again, not C becomes not C. So there's only one change as you move down. If you move down, A becomes not A for each column. And again, as we move across, A remains the same. But we go from not B, not C to not B and C. So not B becomes B. You can see there's only ever one change as we're moving left, right, up and down within the grid. So for variable sum of products can R map. So a 4 variable K map can simplify problems of 4 Boolean variables. 4 inputs. The K map has 1 square for each possible sum of products min term, which would be 16 squares in total. And migrating 1 square horizontally or vertically never results in more than 1 variable changing. Square designations also shown in my diagrams as hex in the blue. On all K-maps, the left and right edges are also a common edge, while the top and bottom edges are also the same edge. Thus, the top and bottom rows are adjacent, as are the left and right columns. So the best way to think about that is like a computer game where you disappear off one side of the screen and you instantly appear on the next side of the screen. So if in like in Pac-Man, where your little character goes one side, disappears on the right, and immediately appears on the left. And that's how we see K-maps. So K-maps, we assume that the left and right edges are actually touching, and also the top and bottom are also touching. So this is important when we try to use the K-map, that we view it in that way, because it's all about adjacencies. If you see those two edges, top and bottom, left and right, as being adjacent, then it will help you use the K-map to simplify, which we'll come on to, but that's the kind of first rule. So this is a 4 variable sum of products can R map, and again you can see that the way we're drawing it out is very specific, with the inputs changing. Only one input changes as we move across, so it's always normally the right input that changes. So we start off, in this case of sum of products, we start off with them all knotted. So C and D are knotted, and then it's D that changes, and then it's after that, so it's right then left. So C changes and then right again, and it's the same with this one. So B changes, that's the one on the right changes, then the one on the left changes, and then the one on the right changes. So it's right left, and if you remember to start at not for SOP and not for POS, then you can't really go wrong as long as you're only changing right left as you move across or as you go down. So just to try and get a handle on how to write these out, there is a pattern to it, of course, and that's reflected in the numbering. So it's just worth, you must make sure you write them and draw them in the same way that I show them here, otherwise they won't work properly. So 4 variable products of sums can R map. Again, simplify problems of Boolean variables. So the K map, only 1 square possible for each max term, 16 in 4 variables. And again, we have migrating from 1 square horizontally or vertically never results in more than 1 variable changing. And on all K maps, the left and right edges. So it's exactly the same as a SOP really, except we're using product of sums. So you can see here, this is the product of sums, and that's what I was saying about them starting out with zeros. So it's A or B or C or D, and as we move down, you'll see again it's the rightmost one that changes first. So it's right, then left, then right. And as we move across here, the right variable changes, then the left variable, and then the right variable. So if you start off with this, you only have to really remember the corner variable positions, which are always, in the case of POS, without knots, but with obviously ORs, and in the case of SOP, with knots. So they're all 0, 0 in this top left-hand corner. And if you do that, the numbering of the squares should always work out exactly the same. So right, left, right, left. So let's go to the exercise sheet, and we can actually draw these out and see how that kind of works. So I'll move over to the exercise sheet. So here we are in the exercise sheet. So drawing out the SOP or POS can R maps. So draw a 2 variable K map in the SOP form with inputs labeled as A and B. Then enter the correct binary hex number created by the inputs for each min term. So this is the first one done. So just 2 inputs, A and then B. So start off in the SOP one, we start off with them both as not A, not B, and then we go to obviously A and B. And that gives us, so these would be, so they're not B, not A, so that must be 0, 0 in the binary. So 2 inputs, both set to 0. This one is B, so that must be 0, 1, which is 1 in the hex. And here we have 1, 0, so that's 2 in hex, and 1, 1, which of course is 3 in hex. So the next thing we're going to do, draw a free variable K-map in the SOP form with inputs labeled as A, B, C. Okay, so free input. So it's SOP, so we want to start off with them all being not. So I'm going to have to input my equation here. Might make it a little bit odd doing it. So this is where it's useful to have a bit of paper, to be honest, and do it by hand. Be a lot quicker than I'm going to be trying to do it in Word, but I'll try and be as fast as I can, of course. So this is A. So remember, start with the not, and then we have oops. So I just need to change that to not B. And remember, with summer products, it's and. And let's do not C. There we go. Right. Excellent. I'm just going to copy that just for speed. Okay, so moving across. So like I say, it goes right, left, right, left. So the right variable is the one we're going to change. So where it was not C, we're now going to make it C. And then we're going to go and make the B, so left now becomes B. And then finally we go right again. Whoops. And C changes to not C. And that's all the combinations of B, C. And then here, well, it's just A and not A, isn't it? So that's easy enough to do. There we go. So not A. Oh, didn't need my not symbol, do I? Just put that in. I didn't need it. So it's just A. Whoops, just A. There we go. And then we can put the binary and hex in. So the binary would be, because these are not, so they must be 0, 0, 0 for each input. Let's do the binary first. So this is 0, 0, 1. Oops. And this is 0, 1, 1. So the first input A is always going to be 0 in this row. And then we have 1, 0. And then we have on this one, it's always going to be 1. Yep, for A input, it's always going to be 1. And then 0, 0, 0, 1. 1, 1 for BC. And 1, 0. And then all we need to do is just convert from the binary to the hex. So it's nice and easy for 0. It's just 0. That's 1. That's 3. That one's 2. This is when your binary to hex conversion comes to its own. That's 4. That's 5. That's 7. And finally, we have 6. Okay, so that's numbering the min-term cells in both binary and hex based on the inputs that are coming in from A, B, C in the same order. So A, B, C. So left to right, writing it out. So next one, we've got a 4 variable K-map, just to practice drawing that out. Again, using sum of products. So we're going to need to draw in these inputs. I'm going to copy this little equation here, just to kind of help speed things up a little bit, if I can. Right, so let's go right across here. So we start off with A and not B. And then we do C, not C. Oh, not C. So not C and D and not D. There we go. So that's our inputs, and then we're gonna change each one of those. So just for speed, copy those quickly across to there so I can alter them. So again, right, left, right, left. So what was not D becomes D, and then it's left one, so that is D now. So that means that C becomes D rather than not C. That, and then finally D, then going back to the right, becomes not D again. And then on the other side, we do the same thing. So right, left, right, left. So B not B, rather becomes just B. And then A, which is not A, becomes A. And then finally B becomes not B again. And then to map out our binary, so again we're starting with all 4 at 0. And then we move across. So then the first 2 here are always going to be 0, 0. That won't change on the row. And then we've got 0, 1. And then 0, 0, because that's always going to be the same. 1, 1. And then 0, 0, 1, 0. And then the binary for this one. So these first 2 bits are not going to change. They're going to be set at 0, 1. 0, 1, 0, 1, 0, 1. And then looking at the columns, again we've got, well, C, not C, they're going to be 0, 0. And that's going to be 0, 1. That's going to be 1, 1. And that's 1, 0. And then here we have A and B, so that's 1, 1 in the row. And then C and D are 0, 0, 0, 1, 1, 1, and 1, 0. And then here we have 1, 0. So 1, 0, 1, 0, 1, 0. And in the last 2, so 1 is 0, 1, 1, 0, 1, 0, 0. So those are all the binary numbers worked out. So now convert those to hexadecimal. So 0 for 0, that's easy. And that's 1. And then we have 3. And then we have 2. And here we have 4. That's 5. That's 7. That's 6. So now we have, what have we got? 4 and 8. So we've got, so it gets a little bit tricky. So we've got 4 and 8. So we've got 12. Now in hex, so A is 10, B is 11, and C is 12. So this is C. And then this is 13. This is D. This is 15. So that's F. So it's 14. So yes, so F on that one. This one is, that's 14, so that's E. This one is 8. That one's 9. That one's 11. And that one's 10. So we should be able to count all the way up to from 0 to F. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, so all the way from 0 to 15. So that's our hexadecimal numbers and our binary numbers for 4 inputs. So now we come down, and now we're doing it in POS form. So to give you practice of doing out a canard map in product of sums. So again, it's just 2 inputs this time, A and B. So let's do that. So remember, this time we're looking for zeros. So and we're using OR as our first level. So let's insert an equation to get started. So A or we're doing 2 inputs, aren't we? So A is all we need. And this one is B. And then we go, so B becomes not B. And A becomes not A. There we go, like that. So then our binary numbers, so it's just 0, 0. 0, 1. And then 1, 0. And 1, 1. So hex values would be 0, 1, 2, 3. And now we've got 3 inputs to do. So just to make it again easier, I'm just going to copy those. A inputs, because that will be the same. And then we need, and copy this. So let's just see if I can put those in. Yeah, okay, so not B. I remember doing OR. So, or C. And then with this one, remember we changed the, it's right, left. So, oops, that's not doing what I want. There we go. So let's just put in so then it becomes not B or not C. Like I said, it's a bit fiddly doing it in Word. Paper and pencil, so much quicker. So not B or C. And then finally, it's yeah, not B or C. There we go. That's it. That's the combination that we need. So so in terms of binary, because we're looking in POS product sums for zeros, A, B, C, or C must be 0. So that's the 0, 0. And so A is always going to be 0 on the input. So that must be 0, 1. That must be 0, 1, 1. And that must be 0, 1, 0. And on this one, that must be 1, not A is 1, 0, 0, 1, 0, 1, 1, 1, 1, and 1, 1, 0. And again, converting those back to hexadecimal, that's 0, 1, 3, 2, 4, 5, 7, 6. So you see the numbers don't change for the max term. So the way the cells are numbered remains the same in product sums as it does in sum of products if you get the layout of the inputs correctly and you're just doing right left as you're changing them from starting in the top left corner at 0. So now we've got the 4 input canal map for POS. So just to save time, let's copy those inputs to start with. And I'll have to re-letter these ones, but do that. Okay, so starting at A, B, and just coming down. Oh, seems to have lost the knot, so that's not so. Oh, I see. It's taken. Ah, right. Okay. See what I did wrong. Trying to be quick. Yeah, it wants to paste it that way. Shortcuts in Word sometimes aren't very shortcutty. So let me just attempt to get my equations sorted out. Right. Okay, so we've got the equation holders there, which is what I wanted. So A or B, C or D. So we're going to go C or D, and then it will be C, not D. And then it will be not C, not D. And then it'll be not C, D. And here we'll go A or B, A, not B. Oops. A, not B, not A, B. There we go. Right. Okay, so that should give us 4 zeros. So 0, 0, 0 is a binary number, which in hex is also 0. Then we will end up with, so this will be 0, 0, 0, 0, 0, 0, and in terms of the pattern, so C 0, 1, 1, 1, 1, 0. So we could put those ones in, so 1, 0, 1, 0, 1, 0. So this is the pattern for the column. Oops. There we go. And for the row, so that's 0, 1, 0, 1, 0, 1, 0, 1, and then this one is 1, 1, and this one is 1, 0. Okay, and again with the hex, that's 1, 3, 2. That's 4, 5, 7, and 6. That one's 12, which is C. That one's 13, which is D. That's 15, which is F. That's 14, which is E. 8. It's 9. That's 11. B. And that's 10, which is A. So we get the same numbering. I mean, I could have just copied the numbers from the other one because I know it's going to work out the same, but I just wanted to go through it. And I suggest you go through it as well, just to get it into your head. Make sure the inputs, you're familiar with the input pattern and how it changes from one square to the next. And you can draw out these canard maps in this way, because if you're going to answer the questions in TCA3, for example, you know, I'm assuming you know how to draw a canard map, and you can draw the inputs in the same way as I'm drawing them here, and I've asked you to do it, and you're numbering the cells the same way as well. And it's really important the cell numbering is correct in line with that. So make sure you get this into your head. I'm only going up to 4 inputs, so you know, 2 inputs, 3 inputs, 4 inputs. Just make sure you're familiar with what we've just done. That's the whole purpose of these exercises, both in sum of products and products of sums, so that you can draw them out yourself on a bit of paper and have them work out exactly as they are here. So I think that's the last one. Yeah, there we go. So we can draw them out now. Let's go back to the presentation. So simplifying then with sum of products and product sums expressions. So we will use the Canard map to simplify Boolean expressions by placing min terms for sum of products or max terms for product of sums values on the map, and then we'll group those terms to develop simpler Boolean expressions. So you can see that how we use the Canard map really is we map our min terms and our max terms onto appropriate Canard map. So here I have two Canard maps, one for SOP as labeled in the top left corner, and one for POS. And I've mapped these terms on it. So the first expression here is obviously the SOP, so it's ANDs into OR, first level. So I've got not A, B, C, so that equates to not A, B, C. So I've put a 1 in that cell. So where these two cells come together on that min term, which is not A, B, C, I've put 1. And then I've looked for not A, not B, but C. So not A, but B, but C. There's 1 there. And here I've got not, and I've got A, not B, but C, and I've put 1 there. So I've mapped the 1s on, and all the other cells obviously become 0s. And then with the product sums, I've done the same thing, but obviously I'm looking for the max terms, which are the 0s. So I've looked for not A, B, or C, which is this one. So I'll put a 0 here. And now I've looked for not A, not B, or C. So I'll put a 0 there. And then finally I've looked for A, not B, or C. So that put a 0 there. And the rest became 1s, of course. So some product sums, you're looking for 0s, and what isn't must be a 1. So you map your max terms or your min terms onto the Canard map. So again, we've got a little exercise for placing the min terms or max terms on the Canard map. So we'll go to the exercise sheet now. So here we are on the exercise sheet. So the first thing is, so look at the following sum of products expression and then map its min terms onto the appropriate Canard map. So we've got a blank SOP K map. So I'm getting you to actually draw it out as good practice, really. To save a little bit of time though, because I've just been practicing it above, I'm going to copy it out from above just to make it a bit simpler and a bit, just to stop it being a bit long-winded, really. So you should write them out the same. So let me just find the Canard map that we just did. So let's see now. What's that? Here we go. There's the SOP Canard map that I previously did. So I'm just going to copy that one, if it allows me to. Okay, so let's copy that out. And we can draw that in. Into this one. There we go. Right, just saves a bit of time. And let's get rid of those. Okay, so let's draw this out. So remember, with sum of products, we're looking for 1s. So we've got to put those into the min terms. So we got, what have we got here? Not A, B, and C, D. So not A, B, there we go. And C, D, which is that square there. Yeah, so where C, D, and not A, B collide, we're looking for 1s, we put a 1. And then we have not A, B, so we're still in that same row. C, not D, so we can put a 1 there. And then we have A, B, so A, B is this one. C, D, so we can put a 1 there. And then finally, in the last min term, we have A, B, C, not D, so it's that one. So all the other cells become 0 once we've identified the min terms in our sum of products. Then we have our zeros left, like that. So that's complete. So we've identified the min terms, and we've got from the expression. And then we've got one for product of sums as well. So again, this time we're identifying zeros. Don't forget, with product of sums, it's zeros. So again, I've got a product of sums that I've already done, but you write yours out that way. So let me just copy that for a bit of speed. That one. Okay, and we don't need the references there for the moment. So again, we need to put these in. So not A or B, so not A or B, that one. And then C, not C or D, not C or D, so it's that one. So 0 there. And then the next max term, we've got A, not A, B, not C, D. There's not C, D, and not A, not AB, that one. So that's a 0 there. And then we go to AB, not C or D. So AB, not C or D, that one. And then we go A, not B, C, not D. A, not B, C, not D, that one. Okay. Oh, sorry, no, that's wrong. No, that's C or not D, isn't it? So C or not D, that one. There we go. That one there. So make sure you map them out correctly. And then obviously the other empty cells they must be 1s. So you're mapping out all the F outputs onto your canard map. Okay, that's good. So that's it. So you should be able to map from expression to your canard map. Back into the presentation. So canard map, some comments. So each square, min term or max term in a canard map is unique, and we can label it in binary, decimal, or hex based on the input. So that's what we were doing before. So we were using binary numbers and hex numbers to identify individual squares within our canard map. You could also do a decimal number as well on there, but I just did binary and hex. We can also designate the Boolean function by the K-map squares it occupies. So this means that we can give a K-map coordinates for any SOP or POS expression. Yeah, so rather than having the full expression, what we're basically saying is I can give you a set of coordinates and say this is for SOP, you just fill in the ones at these coordinates on the canard map. So a canard map expression, or an expression could be given as canard map coordinates, which might look like this. So we put our expression in as F equals sigma, that's a Greek letter, so sigma m, and then in brackets we put our coordinates, and currently I've got them in hexadecimal, so 57DF. So cells on the K map of labeled as 57D and 57 and D and F as their coordinates is where I'm identifying 1 bits in the SOP, or it'd be 0 bits, zeros within a POS, of course. So coordinates are one way of doing it. So coordinates in hexadecimal inside the brackets after the sigma m part. So these are coordinates for the canard maps essentially. So if you were given the sigma coordinates of F sigma m 57df, you could immediately deduce from the SOP that the SOP function was F equals not A, B, not C, D, or not A, B, C, D, or not, A, B, not C or D, and D, or A and B and C and D. So you observe the sigma notations in either SOP or POS completely describe the Boolean function mapped on the K-map as long as one knows what the number of input values or variables there are. So that is important. So we do need to understand the number of variables being used, of course. So that would be expressed as well. So again, we have a little exercise for doing this, and again, if I have an exercise, it means it's going to be in the TCA as a hint. So make sure you're familiar with these coordinate positions. So we'll do the exercise now. So here we are back in the exercise sheet. So canard map coordinates to determine SOP and POS expressions. So again, look at the following coordinates and assume 4 inputs. So I'm telling you the number of variables, so A, B, C, D, and use them to determine the SOP and POS expressions they represent. So I've got 2 tables, one for SOP, one for POS, and a set of coordinates. So I just need to map those coordinates on, and then I should be able to write out the expression based on the coordinates that have been provided for the min terms and max terms for each. So again, I'm just going to copy my POS and SOP tables just for quickness. So we'll start with POS here. Okay, so there's my coordinates. So what you would actually, it would be easier. Let's do it this way. So you need to work out the coordinates first, which I've already done previously. So let's just take a copy of that. Just again for speed, because really, you know, it's just a question. You've done this already if you've been working your way through. So you should be able to do that again without me having to kind of go over it again. So I'm just going to put that in there. So here we have a POS K-map with the coordinates on it. So it's just a question of matching up individual coordinates now to put in, because it's POS, we're looking for zeros. So where's 9? 9 is here. We'll take out that, and that's where our 0 will be. B, where's B? B is here. So put in R0, and D, I think I know where this is going. There we go. So, and F. That's it. So the rest of them, they must be all the ones. Okay, so you see how the coordinates are working. So from a set of coordinates, assuming I have those, I know the coordinates, I can work that out. Oops. I can position my, in this case a POS, my zeros where they needed to be. Okay, and I can do the same then with SOP. And of course, with SOP, well, let's just do it just to prove that. So again, I'll find my SOP previous with the map on it. Okay. So again, same set of coordinates, 9, B, F, and D. But you can see, because the numbers are exactly the same, it's going to give the same position, but this time it's saying SOP, so it's going to be 1s. And the others are going to be 0s. Just like that. Okay, so now we can turn that back into our expression. So let's insert an equation. So what have we got? So F equals open brackets. So our first min term, it doesn't matter which way we put the min terms in, by the way, specifically, but I'll do them in the same order that we had. So so we have 9. Okay, so let's do so this first one for that's the, yes, we're doing the SOP one first. So this one for SOP. So yeah, so we got so that's in A. Oh, need my and not B. And what's above it? So not C and D. Not C. And D. And then we're coming together with or, of course, and then open brackets, and the next one, do that one again. So we can just, again, I'm just trying to shortcut it a little bit. If I can. So A, not B, C and D. Oops. And then, oops, sorry, or. Now we've got A and B. We go up to this one, not C, D, or A and B, C and D. There we go. And that's the complete expression built. And then we can do the same for POS. So again, insert our equation. So F equals and this one we got looking for, it's the zeros, isn't it? So we're not, oh, so we're not doing ands, of course. So what have we got? Not A. So not A, or B, or for this one, C or not D, right? So C or not D. C or not D. And then, and okay, and again, I'll just try and copy that bit just to okay. Okay, so the next one is going across, so still the first part, but this time with not C. C. And then we go up to not A, not B. But we keep that as C or D, or C or not D. Yeah, so not A. Yep. And then finally, this one, which moves across to not C, not A, not B, not C, not D. So it goes to be not. Okay, there we go. That's it. The expression built from our canard map. So we mapped the variables, we mapped the max terms and min terms from our coordinates onto our canard maps, and then we put them back to being the expressions. Okay, so go back to the presentation. So back in the presentation, so some canard map terminology. So any square or rectangle group of cells that is a power of 2, so 1, 2, 4, 8, 16, we would refer to as, in a canard map, as an implicant. All of the groups of squares in the K-map which we're showing here, including the single square, represent the implicants of different sizes. Okay, so all those with this is a SOP canard map, so the ones are the min terms, and we can make different size groups of ones, squares, as long as we're within the powers of 2. 1, 2, 4, 8, or 16, we can call that an implicant group. So prime implicants, so we'll be simplifying Boolean functions by plotting their values on a canard map and grouping them into prime implicants. So a prime implicant is an implicant that covers as many 1 values in the case of SOP or 0 values in the case of POS as possible, yet, and I say as possible, it still must retain the identity of an implicant. So an implicant is a single cell. When you put cells together in a group, you've got to still be within a rectangular or square shape, which represents the power of 2. So here we've got a rectangle of 4 ones. So this is a prime implicant group of 4. Here we have 4 ones, which is a prime implicant group, rectangle of 4. And here we have a square, a rectangular square of 4, which again is a prime implicant group. So you wouldn't have a prime implicant group of 6, because that's not in the power of 2. So it must only be within the powers of 2. And you can't have odd shapes. It has to be a rectangular shape. So you could, because the edges you assume touch, and this is where it's important to remember the edges are adjacent to each other. So these two here could be combined with these two here to create a group of 4. And that would be fine, except you are trying to make the biggest prime implicant group you can, and the minimal number of prime implicant groups. So here I've got 3 prime implicant groups. I've got these 4 coming together to make 1 prime implicant, these 4 coming together to make another prime implicant, and these 4 coming together to make the 3rd prime implicant. Now that's the smallest number of prime implicant groups I can make using all of those implicant cells. So 3 is the best. If I combine these with these, I'd end up with those as one group, and then I'd be left with these 2 as their own, and that one, and then these 2. So I'd have more prime implicant groups basically. So you want the minimum number of prime implicants you can get when you're grouping them up, and that's really important for simplifications. The less groups you have, the greater the simplification you're going to end up with. And that's the purpose really behind all this. So you might be wondering, what's the purpose of this canal maps? I'm just introducing it slowly. So first of all, mapping it out, being able to draw them, being able to put the ones or zeros on based on stop or pause, being able to recognize where coordinates are. Those are all core things that you need to be able to do first. Now we're getting into actually using the canal map by mapping our ones or zeros onto it, and then putting them into these groups to try and aid the simplification. So it's the grouping up of the ones or zeros, depending on stop or pause, into primary implicant groups, which helps us with the simplification of using this canal map. So we also talked about a distinguished cell. So a distinguished is one cell, a single min term or max term that can be only covered only by one implicant cell. So it could be an individual cell. So we've got the blue and the orange there as essentially the orange is the distinguished cell. So it's the one, the blue is the distinguished cell. The essential prime implicant is a prime implicant that covers one or more distinguished implicant cells. So the orange one on this map there. A prime implicant then is the largest square or rectangular implicant of cells occupied by a 1 for SOP or 0 for POS. A prime implicant will have 1, 2, 4, 8 or 16. Now in the case of 16, if you've got 4 inputs, that would be the whole, everything would be 1 in SOP, or everything would be 0. That's what we call trivial, because it's, essentially there's no point really. If you've only got one output and it's always 1 or it's always 0 for POS, then it's trivial because it's a waste of time. So normally the groups would be 1, 2, 4, possibly 8 in SOP or POS on 4 inputs. So again, I've got a little exercise for identifying prime implicant groups, because that's really how you use the canal map. So if we go back to the exercise sheet, so back in my little exercise sheet here, and it's asking us to look at the coordinates and assume 4 input variables and use them to determine SOP and POS expressions first. So I'm just getting you to kind of go back through the expressions and work out the expressions there. In fact, that's actually I've just realised that's the second part of the exercise we just did. So I'm just going to leave that one for you to do on your own, because it's the same as what I went through just a minute ago. I didn't realise there was 2 versions of it. So just use just do that one again. I'm going to skip over it because essentially it's the same as what we've done. So I just didn't realise there was a 2 on the coordinates. So do the coordinates one yourself. You'll be fine on that. So identifying prime implicant groups. So here we've got K-maps for SOP and POS expressions. And so we have to put them into our K-maps, and then we need to circle the prime implicants in each. So again, I've just left these blank for you to fill in and get some practice of setting them up and building the K-maps. So I've left them blank. But again, just for speed, I'm going to copy and paste mine down, because otherwise we're going to be here all day. And you don't really need that, because you've already got me doing it. So let's come down and put those on. Okay, so there we go. So that's POS one. I'll just take those out so I don't get confused. And then I just need a SOP one as well. I've got up here. Okay, so let's put that one in. And get rid of those. Right, okay, so we got our POS and our SOP and our maps. So here's the SOP. Let's do the SOP one first. So what we're looking for, not A, B, not C, and not D, not A, B, is that row? not C, not D. There. So we're looking for ones, aren't we? So we put one there, and then we've got not. So we've got A, B, and then we've got not C, not D. So that's one in there, and then we've got A, not B. So that row. C, D, not C, not C, D. That one, and then we've got A, not B. C, D, which is that one, and then we've got not A, B, C, not D, not A, B, C, not D, that one. Okay, so let's see now if we can make primary implicant groups with those. So I'm just going to draw a shape around them, hopefully to indicate primary groups. So we're trying to make the largest groups we can. So there's just two, so we can make a group. Ooh. Let me just really want any fill on this. There we go. Right, okay. So that's one group, and we can then get another group of two with that one and combining it with this one. So that one and that one we can see as one group, and then obviously we've got a single cell here, which could just be an implicant on its own, but you really want to group it. So you could either group it with that one, or you could group it that one. So you've kind of got a choice really. You can't do 3 because that's not within the powers of 2. So you need to decide which one you're going to group with. So there we go. So I'd end up with groups like that. So I'd end up with 3 groups of 2, which isn't the greatest primary implicant groups you could set, but 3 groups of 2 is some simplification, rather than given that they were all individual. So you had 4 originally, and now you've got 3 groups of 2. So you've gotten from 4 to 3 basically. So that's a simplification of a sort. Let's do the pos one. So A, B, C or D, so there's a 0 there. A or B or C or not D. A or B or C or not D. Oh, that one. So yep. Then we got A or not B, C, D. And then we got A or not B, C or D. Oh, just done that one. Oh, A or not B, C or not D. Ah, that one. Yeah, and then A or not B, C or D. And then we got A or B, not C or D. Okay, right. There. Okay, so again, primary implicant groups that we can create here. Well, the best group that we can do with the pos, and in fact, I'll just take one of these and copy it, I think. Is we could create a group of 4. It does leave a little single one out on its own here, But again, I would not leave it as single. I would make it into a group of 2. Oops. So it's like that. So if you can see that. So a group of 2 and a group of 4 would be what we would get in the POS. So that would group it down to 2. So we had 5 max terms, and we're now essentially down to 2 max terms, two groups. On the other one, there's a SOP. Well, we had 5, and we're down to 4. So not a great simplification, but a little bit. Much better on the POS example. Okay, so that's that simplified there. I've got a couple more to do, just to kind of get in the hang of those. So let me just copy my map again. And the SOP one. I just realised this is going on to. I'm just going on to using them now. So this first bit was about simplifying. Finding the groups. Finding the groups is what you need to do first. And the next thing will be using those groups to simplify the expression. So I guess we could map those out in here. So let's do that. I've probably got some more explanation to do in my presentation, which I'll come back to. But as we are here, let's just do a little bit of mapping out. Okay, so again, let's we've got a SOP and a POS example. So SOP first. So A, B, C, D, that one, followed by A, B, not C, D, not C, D. That's that one. Then we've got A, not B, A, not B, A, not B. Is that one? Not C, not D. Oh, there. Okay. And then we've got A, not B, C, D. That one. And we got not A, not B, C, D. Okay, good. Right, so that's mapped. And then on the POS one, we've got A, not B, that row, CD, and then we've got A, not B, C, not D, and then we've got A, B, C, D, and then we've got no, sorry, got A, B, C, not D. Looking at the wrong one. C, not D. And then we've got A, B, not C, not D. And then we've got not A, B, not C, not D. There we go. So we've got those mapped out. So I'm just going back to the presentation for a second because we'll talk about simplification, I think. So let me just go back to the presentation. So back in the presentation, so talk about primary implicants. So how do we then determine the simplest SOP or POS expression for a prime implicant on a K-map? So the Boolean expression for a SOP or POS prime implicant is determined by creating a new min term or max term whose only variables are those that do not change value. Okay, so variables that don't change from 0 to 1 or 1 to 0 over the extent of the prime implicant. So we're looking for things that don't change effectively. So do not change is what we want. So you're looking for variables that do not change, and these are used for the simplified expression, whilst those that do change, essentially we ignore. So let's just work our way through an example here. Oh, this slide's moved a little bit. I'm just need to alter that. So let's have a tendency to wander around with these expressions sometimes. So if I can, like, it should be over there. So I'll just correct that. I will correct that in the PowerPoint as well. So hopefully that's going to save that change, please. Got quite a bit running on this machine at the moment. Okay, so let's just come back into that. There we go. Right, so you can see here, so since A and B do not change over this, so we look at the primary implement group. So here we have primary implement group, nice 4 primary implement group right in the middle there for SOP, so all the ones. And if we look, what doesn't change on the row? So what doesn't change on the row? So A, not A, becomes A, but B remains as B. So what doesn't change is B. So the B input does not change for this primary implement group. And on the columns, what doesn't change? Well, we go from not C to C, but D remains the same. So D remains the same. So to simplify our expression then, we are looking for things that do not change. So F equals B, and because it's SOP, D. So for this primary implement group, we can just sum it, we can simplify it as B and D. And the reason is because these do not change, they remain fixed. What does change is not C becomes C, and not A becomes A. So it essentially cancels itself out. So the reason we're looking for the ones that don't change is because they're significant. The ones that do change obviously just cancel themselves out. It doesn't matter if it's 0 or it's around 1. It makes no difference to this primary implement group, effectively. So you can just ignore them. So you've simplified your expression. So this, these, we had 4 min-terms. We had an expression that was F equals, and then 4 sets of brackets with 4 inputs in each one. And we've gone down to F equals B and D. And that's a huge simplification. And you might be thinking, what's immediately in your head is like, what happened to A? What happened to C? Well, it doesn't matter. They're completely redundant. So that's what I said earlier when we looked at simplification last week. We talked about Boolean theorems and we talked about De Morgan's law. You know, when you simplify an expression down, you actually find, you know, sometimes that, you know, where you thought you needed 4 inputs, you don't. You just need 2 inputs. That's perfectly legitimate. This is work that we're doing on paper. This is the mathematics of our design. This is our simplification, you know, on paper, what we're going to build. We're not built anything yet. This is just us specifying it out, and we're simplifying it down to get the most economical and efficient design we can. So don't worry if you lose inputs at this stage. That's good. Just means we overspec it. Now we only need 2 inputs, B and D, or whatever we want to call them. But you know, for this implement group, that will work perfectly well if we want that type of output. So, you know, logic simplification for a SOP example. So we simplify a Boolean expression by finding its prime implicants on a K-map. And to do this, we populate the K-map as follows. So for a SOP expression, we find the K-map cell for each min-term of function f and place a 1 in it. We ignore zeros. We circle the groups of cells that contain the 1s. The number of cells enclosed in a circle must be a power of 2 and a square or rectangle shape. And we groups of cells can overlap or use the sides that are adjacent to each other. And each circle group of cells must correspond to a prime implicant of f. So the implicants of f are coordinates. So here we have a set of coordinates. So sigma coordinates here, 4, 6, C and E. We plot those onto a SOP expression. We end up with f equals not A, B, not C, not D, or not A, B, C, not D, or A, B, not C, not D, or A, B, C, not D. We plot those onto the SOP canard map, and we create, again, one prime implicant group. So those 2 adjacent sides, remember, they meet, so we can see that as a group of 4 min-terms altogether. What doesn't change? Well, B doesn't change, and not D doesn't change. So this is going to be, again, really good simplification we can do with this one. And so we create a primary group of 4 cells representing F. So on the AB axis, the cells are 1, whether or not A is 1, or always when B is 1. A is essentially not needed. So on the CD axis, the cells are 1, whether or not C is 1, and always when C is 0. So C is not needed. And the simplified expression for F then, we can simplify to, like I said, F equals B and not D. So working for a POS example, so again, simplifying a Boolean expression by finding its prime implicance on the K-map. And again, to do this, we populate the K-map as follows. So for a POS expression, we find the K-map cell for each max term of function F and place a 0 in it. We ignore 1s. We circle the group of cells containing the zeros. The number of cells enclosed in a circle must be a power of 2, and it must be shaped as a square or rectangle. So I'm saying circle, it just means put a line around it, but it must be square or circle. Groups of cells can overlap. Each circle group of cells corresponds to the prime implicant of the F function. So here again, we got essentially the same example really, but this time with zeros. So zeros were for the expression F equals A, not B, C, D, not A, not B, C, D, not A, not B, C, not C, not D, D, not A, not B, not C, not D. And again, we can make our group of 4, and we can create our primary group, and we can see what doesn't change. What doesn't change here is not B and D. So our expression becomes F equals not B or D in product sums. Actually, another little glitch. I got SOP example, and this is actually a POS example. So sorry about that. There we go. Sums example. Okay. So again, you can do the final simplification now using the exercise sheet. So let's go back to our exercise. So here we're back in the exercise. This is what we just mapped these out, didn't we? So we need to do our prime implicant groups so that we can actually do the grouping on this and build the expression. So we do the SOP one first. So let's create some groups. So I just need a shape. So I can make a group with this one. And this one. So we can make a group of 2. There. This one, I can't do anything with that one. That one's going to have to stay on its own sum. And is that one. So again, there's nothing to combine it to because there's no shell. This one, we can make a group again of 2 that way. So we can make one group of 2 here, one group of 2 here, and these single ones will have to remain as just single implicants. And that happens. So you can't always simplify as much as you might want to. You can only go do what you can. So we can still simplify down from. So we had in this case we had 4. How many minterms we had? We had 5 minterms, and we've gone to 1, 2, 3, 4. We've gone to 4 implicant groups. So we've done a little bit. It'll do a little bit. So the expression for this one would be, and again we can work that through. So F equals, open our brackets. So let's just take, it doesn't matter which order we put them in. So I'm going to do this group here first. So let's see now. What doesn't change? Well, A for this 2 group, A and not B remains the same. What doesn't change here is D. So we can get rid of C for this little primary implement group here. So yeah, so A and not D. And what didn't change was D. So we got rid of the C input on that one. Okay, and oh, D in there, I meant B. There we go, A and B, A and not B, and D. And then for this group, these group of two, we've got what doesn't change. Well, C and D remain the same. What doesn't change on this side though is not B. So not B remains the same. We get rid of A because A goes from not A to A. Oops, keep putting it in the wrong place. Look in there, please. Yeah. Yeah, so not B. And yeah, C and D. So again, we got rid of A on that one. And then the other two expressions, well, they just have to remain the same, unfortunately. So there's no simplification we can do for those ones. So this one here is always going to be not A, B, not C, D. So yeah, so not A, B, not C, and D. Oops. There we go. And the final implicant that we have, this one here. So A and B, C and not D. I'm sorry, I'm struggling a bit with this equation builder in Word. Again, if you're doing this sheet, specifically this week, I strongly recommend just printing it out and doing it on paper and pencil. It's a bit of a pain to do it in Word or something. it does make life tricky. You see, I've just destroyed the whole thing there. So I used to have. You're wondering, you know, because I produced these things. I used to have like hotkeys for some of these commands for the nots and the ands and that. Just easier hotkey commands. But I've changed machines since I last did anything with this, really, and I'd have to set them all up again, and I just haven't quite had the time to do that, or at least the inclination to do it. I think I probably should have done before I started doing this exercise with you, but anyway, you'll get on faster if you do it paper and pencil. There we go, finally. Right, that's it. That's the expression complete. Hey, so great. So that's the SOP expression. And obviously for the POS one, it would be about making the groups as well. So there's a group of 2 here, there's a group of 2 here, and there's a group of 2 there. So I can make 3 groups out of, instead of 5, so 3 instead of 5. So what doesn't change in this group of 2 here? So just group those up so you can see them. So those group of 2. So what doesn't change? So you've got, or A or B remains the same because they're in the same row, and then you've got C or not D or not C. So C changes. So we get rid of C and we're just left with not D. Then the next group we would make. Whoops! Oh, that's blown it. The next group we'd make would be these ones here. Now you might be wondering why I wouldn't go with those 2. Well, the reason I wouldn't go with those 2 is because you'd end up with more groups. So I'm trying to limit the number of groups that I have, or create the smallest number. So doing those 2 and these 2 is the smallest, and then having this one and this one, because this lone one needs to be included. So I can make a group of 2 between these 2. So that would that's the best way round, really. So just trying to do that. So what doesn't change on these 2? Well, A or not B remains the same, but what doesn't change up here is C. So C remains the same. D becomes not D. So D gets cancelled out. And then in this column, we have C or not D. What doesn't change on here is, well, A becomes not A, so A gets cancelled out. So we can simplify a little bit. I think you could write the expression yourself from that. That's as we did from here. So I'm not actually gonna do that. You'll see that in the answers. But that's how I got to the simplification for it. So it's just grouping them together, looking for things that don't change, and then developing the expression to not include the things that did change. So the things that changed get kicked out, and you've simplifying down by the groups become bigger min terms, really, or max terms, depending on it's SOP or POS. So we'll go back to the presentation. I think we're almost there. Okay, so there's procedure then. So sort of summary of Canard maps procedure. Start with a specified truth table or Boolean expression. On the K map, plot 1s for SOP, which are min terms, or 0s for POS max terms. Group implicants together to get the largest set of prime implicants that's possible. Prime implicants may overlap each other. It doesn't have to overlap, but they may. They will always be square or rectangular groups of cells that are, remember, it has to be the powers of 2. So 1, 2, 4, 8, so on. The variables that make up the terms of the new expression will be those which do not vary, so do not change in value over the extent of each prime implicant group. You then write the Boolean expression out again for each prime implicant, and then or for SOP or and for POS together to get the new simplified expression that you're creating. We can introduce a concept of don't cares. So don't cares are interesting and can kind of help us to simplify a little bit further. So here we have an example of don't cares, and let me just alter this slide a bit. Again, my text has kind of wandered off to the side. Not quite why that happens, but it happened. I'll fix it. So here we've got a group of 6 ones. So this is a SOP in our map. We've got ones here, and we might have a whole load of inputs which we just don't care about for whatever reason. Now this again, I'm slightly abstracting, so you have to make the leap that says the reason we don't care is because we don't care. So don't worry at this stage why we don't care. We just don't care about this particular set of inputs for some reason. So we have our zeros, we have our ones, and then we also have a whole 4 sets of, in this case, min terms that we don't care about. We don't care if they're 1, we don't care if they're 0 for whatever reason. It makes no difference to us. So because of that, what we can do is we can utilize that within simplifying out. So we have 6 implicants that we can be shown. So if we had the 6 implicants as they stand, we'd have to make 2 groups of 4. So 2 groups of 4 that overlap, and we could simplify it down to F equals B and C, or B and D. Okay, so that would be a simplification of those 6 min terms. But if we include don't care, suppose for our particular logic system we know that C and D will never be 0 together. Okay, so when C and not D implicants do not matter since they cannot happen, and to show the condition we simply put X's in the column that are essentially our don't cares. So in this case, not C and not D becomes don't cared out, and because of that we could then make a prime implicant group. So as we don't care about them, it doesn't matter if they're 0 or 1, why don't we just include them then? Why don't we just assume they're 1s and add them to our min term group? In which case, going from 6 to 8. So this is great. So if we assume the don't cares are 1s, which because we don't care about them, they could be 1s as well as 0s, include them within our prime implicant group. Now we've got a group of 8, and with a group of 8, we can simplify that expression down further. So for this implicant, it actually simplifies to, well, B. F equals B. So we can make it a lot simpler. So the expression is essentially valid, since the forbidden condition will never allow 2 occupied squares to be occupied. So don't cares can help us further simplify an expression. Now this seems really amazing that you kind of get from, we had 4 input, we had 6 min terms, we had a long expression, we had 4 variables, but now we've just gone to simply F equals B. And that's the beauty of kind of working these things through on paper. The simplest answer to obviously this particular problem, whatever this problem was that we were trying to create the function for, was simply a single switch that's either on or off ultimately, and that's it. That's a simplified version of it. So don't cares are kind of handy. So here's another little example with don't cares. So we assume the Boolean expression is shown in the K-map here. The simplest sum of products expressions for the function then would be F equals not A and B and D, or A and B, D. So we can basically make 2 prime implicant groups with this SOP K-map. However, if we introduce the idea of some don't cares, so if we have some don't cares on here, we could make them 1. So those particular, these particular cells, as you can see with the blue ones, we don't care about those, so we can make those 1s. Does that help us? Well, yeah, because then we can create, a group of 4. So we can get 2 groups of 4 maybe. And again, that kind of helps to simplify the expression further. So don't cares are just an interesting sort of concept. When you're thinking about the practical design of your circuitry, your actual functionality, you might have some combinations of inputs which really don't worry about. But don't cares occur when there are variable combinations represented by squares on a Canard map that cannot occur in a digital circuit or a Boolean expression. And since a square is called the don't care, since it can never happen, we can assign a value of 1 stop to the square, or we can use that 1 to possibly construct larger prime implicants, further simplifying the circuit. You could also assign it the value of 0 in a POS representation. So this isn't specifically SOP. It could be related to POS as well. And circuits or Boolean expressions derived using don't care squares are as valid as any other expression or circuit, essentially. So that was it for this week. It's quite a lot in there, quite a lot to do with the Canard maps and then simplifying expressions down. Make sure your Canard maps, you understand them and you can write them out and draw them out exactly as I've shown you. And you can get from the coordinates to map min terms and max terms to it quickly, and we should be fine for the TCA. Okay, thank you very much for your time. See you again.